we'll see if it has any impact. Okay. Okay, let's go to the iPad. Okay, so I can't comment on whether you guys did it or not, but I do have these instructions up here. So for one, show all working. If you don't show all working, I can't find marks. And I can't award marks. If the calculations are wrong and that there is working, I can at least go and find marks. But if it's just an answer with no working, I can't really help. Include all necessary comments. So this was particularly important for question 1.4. So if you don't tell me what you're doing and you're just putting an equation down, it's not really helping anything because I don't know what you're referring to. All right, so a monopolar negative 500 kV DC high voltage transmission line. Okay, so first of all, negative 500 kV and it's monopolar. Monopolar or bipolar, monopolar means there's only one pole, so it could be negative DC or positive DC. Right, so this is 500 kV, earth conductor, ground conductor is naught. So that will be tied to earth, which is naught. Right. Your vertical height, your bundle height is 30 meters. Your height of your earth conductor is 10 meters above that and 5 meters horizontally. All the conductors have radius of 1.9 centimeters. And I gave you the geometric radius of 30 centimeters. Right. The earth conductor also has a radius of 1.9 centimeters. So question one, the equivalent radius of the conductor, that will just be Rec, or R equivalent. It's just applying that equation. Right, so I came out with the value of 21.28 centimeters. A number of folks forgot their units. That doesn't help. I can't award marks if there's no unit. Right. What actually happens is that you don't put a unit there, and then you use the wrong unit in the next section, and that causes a miscalculation of the results. Right. The next question was the potential coefficients total charge on the conductor bundle and the earth conductors. So your self-potential coefficients, P11 is the self-potential coefficient for the conductor bundle. Again, that's just the equation. P22 is the self-potential coefficient for the earth conductor. So it's just applying the same equation. So there are two conductors here. There's one, there's two. Right, again, it's just applying the equation that's there. The mutual potential coefficients, I got D12 equal to 70 meters, and D12 equal to 11 meters. So the mutual potential coefficients between the two conductors would be the same, P12 equals P21, and it's given by the value there. Right, so again, that was just pulling it from an equation. Where a lot of people went wrong was they thought P11 equals P22. Right, that would be the case if it was a bipolar system. And your heights is equal and your conductors are equal. Etc. So that only works if all the geometric parameters are the same. If you have an arrangement like this, conductor bundle 1, conductor bundle 2, P11 would not be equal to P22. Right, your potential coefficients, you can arrange them as shown here in your matrix. So you'll notice where I've put 5.6 and where I've put 8.35. Right, the next one is where a lot of people went wrong. So in your coefficient table, it's P11 over here, P22 over here. So V1 is actually your negative. It refers to the voltage on the first conductor. V2 would be your voltage on the ground conductor. So where people went wrong, I had this. Right, so it's not bipolar. Or I had this. So this would mean 0 volts on bundle and 500 kV on earth. Right, so it has to be arranged the correct way to get any sort of reasonable answer. Okay, then it's just a matter of the method of determinants. To pull it out, you would have noticed I just used 2 conductors, not 3, because 3 you would still be writing the test. Right, so you've just got to be very careful when multiplying here. If you've done it like I've shown here, you need to be aware of the square there. So normally you could multiply that 1 over 2 E naught into the number and calculate it like that. I've pulled it out, so be aware of shortcuts. So mine's a shortcut, and I've done it like that. If you multiplied it out, it should come out with the same number here. Right. Then your determinant for P1 to determine Q1 and Q2, they will be slightly different. Okay. A quick check. Negative Q on negative conductor. Positive Q on earth conductor. Right. You can see there that there definitely is a charge on the earth conductor, even though there is no voltage. Very cool. Right. Okay, cool. That's just pulling the equations and arranging them correctly for now. The average maximum bundle gradient on the pole conductor and the earth conductor. Right, so the average bundle gradient is this equation here. Right, be careful, it is small r. You're dividing the total charge for the equivalent bundle by your number of conductors in the bundle. Right. So I mentioned previously that part of the idea of a bundle is to lower the electric field. So if you're dividing the charge like that, they'll be interacting and lowering the total electric field. All right, I'll go to a simulation just now to show you that I haven't lied with this answer. Then the average maximum bundle gradient. It's just applying this equation. Right, so the reason behind this is I have mentioned that arranging it in a bundle lowers the electric field, but at some places, so I'm just going to call this E1, E1. Right, so if you just look at the field between subconductor 1 and subconductor 2, E1 is going to cancel E2, whereas E1 will have some addition of E2. So it'll definitely be stronger on the outside because those two will cancel. So that equation just relates that sort of maximum field to the average bundle gradient. If we go back to the question, asked for those two values for the pole conductor and the earth conductor. Where people went wrong, they forgot about the earth conductor. Right. If there's only one conductor, you'll also notice the polarity of the electric fields. So for negative, it's negative. For positive, it's positive. So that's interesting that the earth conductor has a field of 11 kV. The pole conductor has 15 kV. So it's not actually as low as you would think. Right, this is where a lot of folk got a little bit confused. So your relative air density, your standard temperature, your standard pressure. So those are given in the question, but your standard temperature, standard pressure, they're right here. So you can just use those values. You don't have to memorize the wrong value. Okay. So the mark allocation was a little bit off here. It was not meant to be 8 marks, but if anybody did answer this correctly, I would have awarded some extra marks. Just going to draw below this. Right, so that's got positive Q, that's got negative Q. So your electric field is doing that. So if it's positive charge, it's positive E, then you need to look at positive corona. This is negative charge. So the direction of the field is towards the bundle. So you'd look at negative corona. Right, so then you just fill out the calculations, compare the electric fields, and determine whether there was any corona or not on that conductor. So here's where I said include all commentary. So just putting an equation doesn't really help because you don't know what you're referring to. So even just writing earth conductor and then writing the equation helps. Where a lot of people went wrong was they just put all the equations down, including the one for alternating current, and that doesn't help me. I'm not here to interpret. I'm here to see if you've got understanding and reasoning. Okay. Right. I will upload the answers. I probably won't upload all my scratchings, simply because whatever's on the left here is very likely to be misinterpreted as what happens. Okay, so maybe just note those electric fields here, and we're going to go and have a look at the model that I developed a few weeks ago and just check if it's, or how accurate it actually is. Oh, before we get there, I think a few of you guys have done the practical now. So you've seen a bit of sparking in the lab, and you've heard that sound, the buzzing sound. Is that correct? We can all recall that.
Yes, yeah.
Okay, so the buzzing sound, when you look at it through a UV camera on a conductor, it's actually little discharges that are occurring. Right, so this is actually corona on the conductor. This is a UV image of the corona on the conductor. So now if you recall the practical, it was kind of a crackling sound all the time. And you can see those discharges occurring, and that leads to that crackling sound. You can see it's all around the surface of the conductor. A little bit further away, there's not much going on. Okay, so that's corona. We need the right voltage or the right gradient for that to occur. Right, I developed this a few weeks ago. I've just put the values in. So this is for what we did in the test. Just trying to make it a bit bigger so you guys can see. So it's probably not too clear, but you can all see my pointer pointing around the conductor bundle. Okay, I'll zoom in now, but just where my mouse is, my pointer, there's a conductor bundle. At the top there's the earth conductor. So if I zoom into the conductor bundle, there it is. Right, so what you can see, they are the 4 conductors, part of the conductor bundle. Inside of that conductor, the electric field is 0. Maxwell's equations tells us that's correct. If your charge is all on the surface, it cancels out in the middle. Similarly, in the middle of that bundle, the electric field is quite low, and that's because all those conductors with the divided charge on them are basically cancelling the electric field there. If you look on the outside of those conductors, you can see there's that red bit. Right. So if we zoom in on the outside of that conductor, there's your sharp electric field. Right. So when that's high enough, corona will occur on the outside of that bundle. Right. So that was the negative polarity one. If I zoom into the earth conductor, right, there it is there. So you can see there's definitely electric field. It's not 0. It's somewhere, it's probably quite close to just over 10. We did calculate it to be 11. There are some issues with this sort of simulation. If the gradient might not be accurate enough, but you can see it's just over 10. So it's close to the 11 that we calculated. Right. Just going to show you the potential. So there we have a minus 500 kV. We've got our naught in red over there. Our bipolar solution is different. That's where you've got your conductor bundles at the same sort of geometric height from the Earth. In this case, you can see I've got positive and negative. And again, if we have a look at the electric field, for positive, the electric field shouldn't be any different. It'll just be a matter of a different polarity. Let's see if we can actually see the polarity. Maybe not. Oh, there we go. Right, so there's an example. You can see the electric field is going away from the positive and towards the negative. Okay. All right. Any questions from your side about that? It's all kind of simple if you get the right things in the right places, isn't it?
So can you hear me?
Yep.
I just wanted to ask one question
Yep.
with the test. So the earth conductor, it showed that it had a charge with no voltage.
Yep.
How come it does that?
So that's normal. So Gauss's law says that charge must be neutral somewhere. So
Yeah.
charge is basically everywhere.
Oh, okay.
Yeah. So charge is basically everywhere. If you did a big, like kind of integration around the area, charge has to be neutral. So that's why, yeah, it kind of it holds a charge, opposite polarity to the conductor bundle. It is actually a little bit more complicated than I've shown there. You're unlikely to get that amount of charge on a single conductor, because remember that your Earth is also at 0 volts. So some of that charge actually sits on the Earth as well.
Okay. Okay. Thank you.
Yeah. Should have just answered physics, right? Right. I think you might have recalled in HV1, I kept on going on about electric field is dependent on charge rather than on voltage. Voltage is just a potential difference, maybe between two charged objects. Okay, cool. I'll stop there.